There is something protecting you right now that you have never seen, never felt, and never once thought to thank. It has no color. It has no sound. You cannot taste it in the air or feel it against your skin when the wind changes direction. It does not appear in any photograph ever taken of the Earth from space, at least not in any light your eyes are capable of perceiving. And yet, without it, the atmosphere you are breathing would have been stripped away billions of years ago by the same star that warms your face on a clear afternoon. Without it, the water in the oceans would have been slowly scattered into space, molecule by molecule, over geological time, until nothing remained but a dry and irradiated rock hurtling silently through the void. Without it, the very chemistry of life, the fragile, improbable dance of proteins and membranes and electrical signals that constitutes everything you are, would never have been possible in the first place. This thing is called the geomagnetic field, and right now, as you read these words, it is weakening. Not slowly, in the comfortable geological sense that lets us treat planetary processes as remote abstractions. Not in some far future that belongs to other generations, other centuries, other civilizations. It is weakening now in measurable increments across your lifetime and the lifetimes of your parents and grandparents. It has lost roughly 9% of its total intensity in just the last 170 years. A span of time so short in geological terms that it barely registers as a whisper in the deep record of the Earth. But in human terms, in technological terms, in civilizational terms, it is a number that should stop you cold. 9% in 170 years. Do the math. Follow that line forward. Ask yourself what it means. Before you answer, before you even try to calculate what lies ahead, consider first what it means to live inside something you have never been taught to see. Consider what it means that the entire edifice of human civilization, every satellite orbiting the planet, every power grid spanning a continent, every navigation system guiding aircraft over oceans, every migratory bird crossing hemispheres, every whale navigating featureless deep water, was built in the shadow of a force that most people never knew existed. We designed everything we have for a world with a specific magnetic envelope. We have never once, in all of human history, had to design anything for a world without one. And the geological record, etched into volcanic rock, preserved in the magnetized sediments of ancient ocean floors, written in the mineral memory of the planet itself, tells us clearly that the field does not simply weaken and then stabilize. Sometimes it weakens all the way down. Sometimes it collapses. And then it comes back, but pointing in the opposite direction. North becomes south. South becomes north. The compass, if anyone were still alive to hold one, would spin and find a new truth. This is not science fiction. It has happened hundreds of times in the history of the Earth. It will happen again. And the question that nobody has yet been able to answer with any certainty is the one that should be keeping scientists awake at night. Is it beginning to happen now? If this kind of question reaches something deep inside you, if the idea that reality contains layers of invisible consequence that we have never prepared for genuinely fascinates and disturbs you, then stay. Subscribe to this channel, leave a like, and let's follow this thread together, all the way down into the dark. Because the story of the Earth's magnetic field is not a story about physics. It is not a story about geology or satellite engineering or migratory biology, though it touches all of those things with devastating intimacy. It is a story about the profound and terrifying fragility of everything we assume to be permanent. It is a story about a civilization that built its entire future on a foundation it never thought to inspect. And it begins, as so many of the most important stories do, not with a catastrophe, but with something far more unsettling. A quiet, slow, almost imperceptible signal that something ancient and fundamental has begun to shift. There is a region in the South Atlantic, spanning parts of the ocean between South America and Africa, where the magnetic field is already dramatically weaker than anywhere else on Earth. Satellites passing through it malfunction. Their instruments behave erratically, as if briefly confused by the space they are moving through. Astronauts aboard the International Space Station, when their orbit carries them across this zone, report something extraordinary. Flashes of light inside their closed eyes. Not metaphorical flashes. Not visual artifacts from fatigue or stress. Actual photons, or rather, actual high-energy particles moving so fast and with such penetrating force that they pass directly through the hull of the station, through the visor, through the eyelid, and interact with the retina without any prior announcement. Cosmic radiation, moving through biological tissue as if the tissue were barely there, as if the armor had already failed. This region is called the South Atlantic Anomaly, and in recent decades, it has been doing something that no model predicted with sufficient urgency until it was already happening. It has been growing, drifting westward, and, most troubling of all, beginning to split. What was once a single weakened zone is now separating into two distinct centers of magnetic depression, like a wound pulling open at its edges. Researchers watching this process have noted the unmistakable structural signature of something the geologic record has captured before, the precursor pattern of a geomagnetic reversal. Not proven, not confirmed, not something any scientist will say with certainty is inevitable on a human timescale. But the pattern is there, the signal is there, and the history of the planet is unambiguous about what a pattern like this has meant before. To understand what a geomagnetic reversal actually is, to truly feel the weight of it, you first need to understand what the field actually does. Not in the abstract mechanical sense of textbook magnetism. You need to understand it the way you understand shelter. As the difference between being inside and being outside, between being protected and being exposed, between a world where life can persist and a world where it cannot. Imagine the Earth wrapped in an invisible magnetic cocoon, extending tens of thousands of kilometers into space, deflecting the solar wind. The continuous stream of charged particles flowing outward from the sun at hundreds of kilometers per second. Without this deflection, those particles would bombard the upper atmosphere directly, stripping away lighter molecules, ionizing gases, gradually eroding the thin chemical layer that makes the surface habitable. Mars had a magnetic field once. The geological evidence is there in the rock, in the ancient magnetized minerals that still record the orientation of a field that no longer exists. Mars lost its internal dynamo, the mechanism that generates the field, billions of years ago. And today, Mars has almost no atmosphere. Its surface is a cold, irradiated wasteland, scoured by cosmic rays, bathed in ultraviolet radiation, as inhospitable to the kind of life that evolved on Earth as the surface of the Moon. That is what the field prevents. That is what the armor is for. And that armor, right now, tonight, as you exist inside it, without awareness or gratitude, is showing cracks. The question is not whether those cracks mean the end. The question is far more nuanced, far more layered, and in many ways far more disturbing than simple catastrophe. Because the Earth will survive whatever its magnetic field does. It has survived every reversal before. The planet doesn't care. The rocks don't care. The oceans, given enough time, don't care. What has never had to face this process before? Not once, not in any form, not in any guise, is a global technological civilization utterly dependent on the stability of a magnetic environment that is now, for the first time in human history, measurably, undeniably, and irreversibly changing. We are not standing at the edge of an abyss. We are standing inside a very old, very slow process, one that was already underway long before any of us were born. And we are only now beginning to look down. To understand the machine that generates the field, protecting every living thing on this planet, you have to begin by traveling somewhere no human being has ever gone, and no human instrument has ever directly reached. You have to go down. Not down in the way you go down a staircase, or into a mine, or even into the deepest ocean trench. Those depths, impressive as they are superficial in the most literal sense. The deepest mine ever excavated by human hands reaches about 4 kilometers below the surface. The deepest borehole ever drilled, a Soviet project in the Kola Peninsula that took decades of effort and eventually had to be abandoned when the rock became too hot and plastic to continue, reached about 12 kilometers. 12 kilometers. In a planet whose radius is over 6,000 kilometers, that is less than a scratch, less than a nick in the outermost layer. The distance from where we have physically penetrated the Earth to the place where the magnetic field is actually generated is roughly equivalent to the distance between where you are sitting and the other side of the world. Down there, 3,000 kilometers beneath your feet, beneath the ocean floors, beneath the roots of mountains and the basement rock of continents, the planet has a liquid interior. Not liquid in the way water is liquid, with its gentle surface tension and its easy evaporation. Liquid in the way that only extreme conditions can produce. Iron and nickel, maintained in a molten state not because of temperature alone, but because of the crushing pressure of everything above pressing down with a force so immense that the very concept of solid and liquid becomes ambiguous. The outer core of the Earth is a vast, slowly churning ocean of metallic fluid, thousands of kilometers deep, at temperatures approaching 5,000 degrees Celsius, roughly the temperature of the surface of the Sun. And it is moving, constantly, slowly, in patterns shaped by the planet's rotation and the heat escaping from the even deeper solid inner core below. This ocean of liquid metal churns and convex and flows in great slow currents that no camera has ever captured and no probe has ever measured directly. This motion, conducting metal in motion, generates electricity, and electricity in motion generates magnetism. The outer core is, in the most fundamental physical sense, a self-sustaining electromagnetic dynamo, converting the thermal energy of the planet's interior into the invisible magnetic structure that extends from pole to pole and outward into space. The technical name for this process is the geodynamo. The informal way to think about it is this: inside your planet, right now, there is something analogous to the coil of wire inside an electric motor. Except the coil is made of liquid iron. The motor is the size of Mars, and it has been running continuously for at least 3 billion years. But here is the crucial thing about this dynamo. It is not stable. It is not a simple, well-ordered mechanism like a clock or a compass. It is a turbulent, non-linear, chaotic system, in the precise mathematical sense of those words, subject to instabilities and fluctuations that emerge from the complexity of fluid dynamics at planetary scale. The flow patterns in the outer core are not fixed. They shift. They evolve. They occasionally reorganize in ways that alter the structure of the field they produce. And sometimes, not often, not predictably, but with a regularity that the geological record makes unmistakable, those reorganizations become radical enough to flip the entire polarity of the field. To make this concrete, to give it the weight it deserves in your imagination, consider the following. You are standing somewhere in the northern hemisphere. The ground beneath you has been there for millions of years. Somewhere in that ground, in an ancient lava flow from a volcano that last erupted before humans existed, there are minerals that crystallized from molten rock and, as they cooled through a specific temperature threshold, locked in the magnetic orientation of the field as it existed at the moment of their formation. They are tiny compasses, frozen in stone. And if you could drill into those ancient flows and extract those minerals and measure their orientation, you would find that some of them point south. Not toward the geographic South Pole, toward where magnetic south was, which, in those ancient moments, was where magnetic north is today. Hundreds of these reversals have been recorded in the rock. Not speculation, not inference. Direct physical measurement of magnetic memory in stone. The history of the field's polarity is written across the planet in stripes of alternating orientation, most visibly in the ocean floor spreading away from mid-ocean ridges, where new rock continuously forms and captures the field direction at the moment of its creation. These stripes were one of the key pieces of evidence that confirmed the theory of plate tectonics in the 1960s. They are one of the most beautifully legible passages in the entire geological record. And what they say, with the calm certainty of physical law, is this: the field reverses. It always has. And the time between reversals, while variable, averages something in the range of several 100,000 years. The last complete reversal happened approximately 780,000 years ago. It is called the Brunhes-Matuyama boundary, named for the scientists who first identified it. Before that, there was another reversal, and another before that, and before that. The pattern is irregular but unmistakable, stretching back through time to the earliest moments when the planet had a solid mineral record to preserve, 780,000 years ago. And the average interval between reversals is roughly 250,000 to 300,000 years. You do not need to be a geologist to feel what that arithmetic implies. But before you allow the word overdue to settle too comfortably into your understanding, consider what it actually means for the reversal process to be underway. It is not a switch being flipped. It is not a moment when every compass on Earth simultaneously spins and points in a new direction. It is a process, long, disorganized, chaotic, during which the field does not simply invert cleanly from one polarity to the other, but instead passes through a period of dramatic weakening and structural fragmentation. The field lines, instead of running in orderly loops from pole to pole, become tangled and multiple. There can be several magnetic poles simultaneously. The overall intensity of the field can drop to 10%, or possibly even less, of its current strength. And this transitional period, this window of magnetic instability, can last not for years or decades, but for thousands of years. 10% of the current field, for thousands of years. To feel the scale of that exposure, consider what even minor solar storms do today, with a full-strength magnetic field in place. In 1989, a geomagnetic storm caused by solar activity collapsed the entire power grid of the province of Quebec in under 90 seconds. 6 million people lost electricity. The storm was not exceptional by the standards of solar activity. The field was at essentially full strength. The damage was catastrophic regardless. In 2003, during what became known as the Halloween storms, solar eruptions triggered geomagnetic disturbances that disrupted satellites, caused power fluctuations across Europe, and forced the rerouting of polar airline flights. Again, full-strength field. Again, significant disruption. Now, imagine a field at 10%. Imagine solar events of similar or greater magnitude striking an atmosphere with almost no magnetic defense. Imagine the auroras, those beautiful, gentle lights that today appear only at high latitudes, descending to the equator and below, visible from the tropics, not as spectacle, but as symptom. Imagine the particle bombardment of satellites not as occasional malfunction, but as continuous attrition. Imagine the effect on the ozone layer, which is itself vulnerable to particle radiation in ways that have direct consequences for ultraviolet exposure at the surface. And now, before you dismiss all of this as distant geological abstraction, come back to the present. Come back to the South Atlantic Anomaly, moving and growing and splitting. Come back to that 9% loss in 170 years. Come back to the astronauts reporting flashes of light in their eyes as they pass over an ocean where the armor has already, partially, locally, thinned. The machine is still running. The dynamo is still turning. But somewhere in the churning darkness, 3,000 kilometers below us, in the liquid iron heart of the planet, something has changed. Some pattern in the flow has shifted. Some structure in the field has begun to reorganize. And we, sitting here on the surface, in our cities and our networks and our technological dependencies, are reading the first lines of a message written in a language that the planet has spoken many times before, but that no human civilization has ever had to translate. There is a map that most people will never see in any school, in any textbook, in any standard presentation of how the Earth works. It is a map of the planet's magnetic field strength, rendered not in the familiar colors of geography, the greens and browns of land, the blues of ocean, but in the cold gradients of field intensity, from deep magnetic blue, where the field is strong, to pale, almost ghostly yellow, where it is weak. And when you look at this map, when you really look at it, something immediately disturbs you, because the planet it shows does not look like the planet you were told you live on. It is not symmetrical. It is not orderly. It does not show a smooth, uniform shell of magnetic protection distributed evenly from pole to pole. It shows something more like a worn garment, thicker in some places and threadbare in others, with a large, unmistakable pale zone sitting over the South Atlantic like a bruise that has been spreading slowly for decades. That bruise is the anomaly. And when you trace its edges and compare them to maps from 10 years ago, and 20 years ago, and 50 years ago, you can see with your own eyes that it is not the same shape it was. It has grown, it has drifted, and now, and this is the detail that makes geophysicists choose their words very carefully when they speak publicly about what they are observing, it has begun to divide. The splitting of the South Atlantic Anomaly into two distinct lobes was first clearly documented in satellite data analyzed in the early 2020s, though the trend had been visible for years before that to anyone looking closely. The two centers of minimum field strength, the deepest points of the bruise, where the armor is thinnest, are now physically separating, moving apart from each other as if pulled by opposing currents deep in the liquid core below. One lobe sits roughly over the South Atlantic. The other is drifting toward the southwestern coast of Africa. And the models that attempt to explain this behavior point toward a specific structure in the outer core, a region where the flow of liquid iron is anomalous, where something in the convection pattern has reorganized in a way that disrupts the orderly generation of field lines in that sector of the planet. To understand why this splitting matters, why it is not simply a curiosity, but potentially a diagnostic signal, you need to understand something about how reversals have looked in the geological record just before they happened. And this is where the story becomes genuinely vertiginous, because the rock record does not show clean, sudden flips. It shows transitions. It shows periods, sometimes spanning thousands of years. during which the field structure becomes increasingly complex, increasingly multipolar, increasingly irregular. Periods during which the simple north-south dipole that we are accustomed to weakens, and secondary magnetic features, additional poles, regional anomalies, wandering centers of intensity, begin to proliferate across the surface of the planet. That is what a reversal looks like from the outside, from the geological perspective of time looking backward. A growing complexity, a fragmentation of the orderly structure, an anomaly that spreads. But there is something even more specifically troubling about the current situation. Researchers studying the deep structure of the core using seismic tomography, a technique that maps the interior of the Earth using the way earthquake waves travel through different materials, have identified a massive anomalous region in the lower mantle beneath the African continent. It is called the African Large Low Shear Velocity Province, and it is one of two such structures known to exist in the deepest part of the Earth's mantle, just above the outer core. These structures, enormous, poorly understood, possibly ancient remnants of primordial material from the planet's earliest history, appear to influence the way heat flows out of the outer core and into the mantle above it. And the region beneath Africa, where this structure sits, is precisely the region that corresponds, on the surface above, to where the South Atlantic Anomaly is most active, most dynamic, most distorted. This is not coincidence. This is not noise in the data. This is the deep interior of the Earth, the part we cannot reach, the part we have never directly sampled, the part that operates on timescales so vast that human civilization is less than a rounding error in its history, actively shaping what is happening on the surface, in the field, in the satellite data, in the eyes of astronauts blinking in surprise at lights that have no right to be there. The scale of what we are actually talking about here deserves a moment of stillness. 3,000 kilometers below the surface, there is a region of rock and semi-liquid material the size of a continent, possibly several continents, that has been sitting in roughly the same position for perhaps 1 billion years or more, subtly distorting the thermal dynamics of the liquid iron ocean above it, nudging the convective currents that generate the field, applying a slow and patient pressure to the geodynamo that has been accumulating across geological time. And that accumulated pressure is now, in this specific century, in this specific era, expressing itself as an anomaly that grows, drifts, and splits in patterns consistent with the earliest stages of a magnetic transition. Let that settle for a moment. 1 billion years of slow geological pressure, releasing its consequence in a window of time that overlaps with the existence of smartphones. And yet, this is still only part of the picture. Because the South Atlantic Anomaly, dramatic as it is not the only signal. The magnetic poles themselves, the north and south magnetic poles, the points on the Earth's surface where the field is directed vertically downward or upward, have been moving for as long as we have been measuring them. The North Magnetic Pole was first located by the British explorer James Clark Ross in 1831 in the Canadian Arctic. For most of the 2 centuries since, it drifted slowly, perhaps a few kilometers per year, in a roughly predictable pattern. But beginning in the 1990s, something changed. The pole began accelerating. By the early 2000s, it was moving at nearly 50 kilometers per year. By the 2010s, it had crossed the Arctic Ocean and was heading toward Siberia at a speed that forced aviation authorities and navigation system operators to update their charts more frequently than any previous historical period had required. 50 kilometers per year. Where it was once sufficient to update navigational magnetic charts every few years, the acceleration of the pole made annual updates necessary. The International Association of Geomagnetism and Aeronomy, which maintains the World Magnetic Model, the mathematical description of the field used by virtually every GPS device, every military navigation system, every commercial aircraft autopilot on Earth, was forced to release an emergency update ahead of schedule in 2019 because the model's predictions had drifted outside acceptable accuracy limits faster than anticipated. This had never happened before. Emergency updates to fundamental planetary models are not routine events. They are signals. What is driving the polar acceleration? The same thing driving the anomaly. Deep in the outer core, beneath the Arctic and beneath the Atlantic, the flow patterns of liquid iron are changing. Specifically, researchers have identified what they describe as a jet stream in the outer core, a fast-moving current of liquid metal circling the inner core, similar in some ways to the atmospheric jet streams that drive weather patterns in the upper troposphere, except that this one is made of iron, moves at the speed of centimeters per year rather than hundreds of kilometers per hour, and influences not the path of storms, but the orientation of the entire planetary magnetic field. This jet has been accelerating. Its interaction with other flow structures in the outer core is pulling magnetic flux concentrations, the roots of the poles, away from their historical positions, dragging them across the surface at speeds that no geophysical model predicted a generation ago. And the same dynamics that are accelerating the North Magnetic Pole are, in all probability, connected to the same deep structural reorganization that is driving the growth and splitting of the South Atlantic Anomaly. One signal could be coincidence. Two signals in the same system, pointing in the same direction, driven by the same underlying cause. That is something else. That is a pattern. And the Earth, in the patient and indifferent language of geophysics, has been writing this pattern clearly for anyone willing to read it. We are not watching a stable system with local irregularities. We are watching a global system in measurable, accelerating transition, moving in ways that are unprecedented in the entire span of recorded human observation, driven by forces that operate at depths and temperatures and timescales that dwarf everything our civilization has ever built or imagined. And the further you follow this pattern, the more carefully you trace each signal back to its origin, the more a single, enormous, unavoidable question rises to the surface like a pressure wave from the deep. What happens next? And are we, any of us, remotely prepared for the answer? Here is the central paradox that nobody in the public conversation about the Earth's magnetic field ever seems to confront directly. We do not actually know what a geomagnetic reversal does to life. Not with certainty, not with the kind of empirical, evidence-based precision that would allow us to say, here is the threshold, here is the mechanism, here is the timeline, here is what you should expect to experience. The geological record tells us that reversals have happened hundreds of times. It tells us when they happened, roughly how long they took, and what the field looked like before and after. What it cannot tell us, what it is structurally incapable of telling us, is what the world looked like during. What it felt like, in the biological sense, to exist inside a planet whose magnetic protection was fragmenting in slow motion over millennia. Whether life thrived, struggled, or was selectively devastated. Whether the atmosphere thinned measurably, whether extinction events clustered around these transitions in ways that matter. Researchers have looked. They have looked carefully with increasingly sophisticated tools at the correlation between magnetic reversals and mass extinctions, between reversals and changes in ocean chemistry, between reversals and shifts in species diversity recorded in the fossil record. And what they have found is contested, uncertain, suggestive in some analyses, inconclusive in others. Some studies identify a statistical correlation between reversal events and elevated extinction rates. Others find no robust signal. Some researchers argue that the transitional weakening of the field would expose the surface to enough additional radiation to meaningfully elevate mutation rates and damage ecosystems. Others counter that the atmosphere itself provides substantial shielding even without a magnetic field, and that the biological consequences may be far more modest than intuition suggests. This is not the comforting uncertainty of a solved problem with minor details remaining. This is the uncomfortable uncertainty of a question that remains genuinely open in the most rigorous scientific sense, because the tools we have for reading the past simply cannot resolve the answer at the resolution we need. We cannot drill a core sample from 780,000 years ago and find preserved in it the radiation dosage experienced by a mammal at the surface during the reversal transition. We cannot interview the organisms that lived through it. We cannot run a controlled experiment with a planet. And here is where the paradox deepens into something almost philosophical. In the absence of certainty about the past, we are forced to reason about the future using models. And those models, as powerful and sophisticated as they have become, are built on assumptions derived from a system we have never fully observed in transition. The geodynamo models that attempt to simulate the behavior of the outer core are some of the most computationally demanding in all of science. They require supercomputers running for months to simulate decades of core behavior. And even then, the simulations are necessarily simplified. They cannot capture the full turbulent complexity of the real system at the spatial and temporal scales that matter most for predicting field behavior. What this means in practice is that when scientists attempt to predict whether the current weakening of the field represents the beginning of a full reversal, or merely an excursion, a temporary dip and partial flip that corrects itself without completing, the honest answer is that they cannot yet tell the difference from inside the process. A reversal and an excursion can look identical in their early stages. The diagnostic signatures that distinguish them reliably only become clear in retrospect, when the full geological record of the event is available to be read. Which means that the only way to know whether what is happening now is a reversal is to wait, possibly for centuries or millennia, and see whether the field recovers or continues to collapse. We are, in the most literal sense, inside an experiment whose results are not yet available. And we cannot pause it, cannot accelerate it, cannot influence it in any way. The forces involved are planetary in scale and geological in duration. They operate entirely beneath the threshold of any human intervention. Whatever the geodynamo decides to do, it will do it on its own terms, in its own time, with complete indifference to the civilizations sitting on the surface above it. But here is where the paradox sharpens into something with immediate, practical, uncomfortable edges. Because even if we accept the full range of scientific uncertainty, even if we grant that this might be an excursion, might stabilize, might resolve without a full reversal, the current state of the field, right now, today, is already causing problems. Not future problems, present ones. The South Atlantic Anomaly is not a theoretical future threat. It is an operational reality that space agencies have been managing, quietly and with increasing urgency, for decades. The European Space Agency's Swarm satellite constellation, the most detailed continuous measurement of the Earth's magnetic field ever attempted, has been providing real-time data on the anomaly's behavior since 2013. The data it has returned is not reassuring. The anomaly is not static. It is not stabilizing. In the years since Swarm began its measurements, the minimum field strength within the anomaly has continued to decrease. The overall area of anomalous weakness has expanded, and the division into two lobes, the splitting, has become increasingly pronounced. Satellite operators have developed specific protocols for managing their spacecraft as they pass through the anomaly. They power down sensitive instruments. They reduce the operational complexity of their systems. They accept a higher rate of single-event upsets. the technical term for the random bit flip errors in electronic memory that occur when a high-energy particle passes through a semiconductor and flips a 0 to a 1 or a 1 to a 0. These errors are manageable today, with a field at 91% of its historical strength. They become less manageable if the field continues to weaken, and they become potentially catastrophic for satellite constellations, for GPS networks, for communication infrastructure. If the field drops to the levels associated with a full reversal transition, the Hubble Space Telescope was designed with the South Atlantic Anomaly specifically in mind. Its operators developed an avoidance protocol, essentially a rest mode that the telescope enters when passing through the anomaly, because the increased radiation environment in that region was damaging its instruments. The Hubble is one of the most carefully engineered and meticulously managed scientific instruments ever built, and even it cannot simply operate normally through the anomaly. It has to go quiet. It has to wait. Now, consider that the anomaly is growing. Consider that the field outside the anomaly is also weakening, globally, diffusely, measurably, and consider that since the Hubble was designed, the world has placed into orbit, conservatively, tens of thousands of additional satellites. The commercial satellite constellations now being deployed by private companies represent a qualitative change in humanity's dependence on orbital infrastructure. Hundreds of satellites simultaneously providing broadband internet, GPS augmentation, weather monitoring, financial transaction timing, and military intelligence. Systems designed for a world with a specific magnetic envelope. Systems for which no redundancy plan exists that does not depend at some level on the stability of that envelope. This is the true shape of the paradox. Not the geological question of whether a reversal is coming. Not the biological question of what it will do to living organisms, but the civilizational question of what it means that we have built, in the last 70 years, a global infrastructure of extraordinary sophistication and extraordinary fragility. Fragility not to natural disasters on the surface, not to storms or earthquakes or floods, but to the behavior of forces that originate 3,000 kilometers below the surface and express themselves in the space between the Earth and the Sun. We built our civilization in the shelter of an invisible fortress. We built it assuming the fortress was permanent. We built it without ever once checking the walls. And now, for the first time in human history, someone has gone and checked. And what they found written on those walls, in the patient language of declining field strength and drifting poles and spreading anomalies, is a message that no civilization has ever had to read before. The fortress is not permanent. It never was. It just seemed that way, from inside, in the brief moment of geological time we happen to occupy. And what we do with that knowledge, whether we even acknowledge it clearly enough to act, may be among the most consequential decisions a technological civilization has ever faced. Before there were compasses, there were birds. Long before any human civilization understood what magnetism was, long before the first lodestone was suspended on a thread and observed to align itself with an invisible force, the Earth's magnetic field was already being read, interpreted, and navigated by biological systems refined across hundreds of millions of years of evolution. The migration of birds across continents, the navigation of sea turtles across featureless ocean, the foraging routes of bees measured against the geometry of flowers and sunlight, the deep-sea journeys of whales following corridors invisible to every instrument we would eventually invent. All of these systems, and dozens more, from bacteria that orient themselves along magnetic field lines to salmon returning unerringly to the rivers where they were born, are built on a biological sensitivity to the geomagnetic field that is so precise, so deeply embedded, so functionally critical to survival, that its disruption represents not merely an inconvenience, but an existential threat to the organisms that depend on it. The study of this sensitivity, magnetoreception, is one of the most quietly extraordinary chapters in modern biology. For decades, scientists knew that animals were navigating in ways that could not be explained by any known sensory system. The evidence was overwhelming, and the mechanism was unknown, and the combination of those two facts produced one of the most sustained and productive scientific mysteries of the 20th century. Birds released in unfamiliar territory, far from any recognizable landmark, with no access to celestial cues, still oriented correctly toward their migratory destinations. Sea turtles, hatching on beaches in the Caribbean, navigating across the entire Atlantic Ocean and back over the course of decades, returning to the exact beach where they were born with a positional precision that defies any explanation that does not involve sensing the field directly. We now know that the mechanism exists, though we still do not fully understand all of its forms. Magnetite, the same iron oxide mineral that makes compass needles work, has been found in the tissues of numerous animals, in the beaks of homing pigeons, in the heads of salmon, in the bodies of honeybees, in the skulls of dolphins. These biological magnetite crystals can function as microscopic compass needles, allowing the nervous system of the animal to sense both the direction and the inclination of the field. The angle at which field lines intersect the Earth's surface, which varies systematically from equator to poles and provides a form of latitudinal information. A sea turtle, navigating in open ocean, may be reading not just direction, but position. Using the field as a map, as well as a compass, triangulating its location from the local characteristics of the magnetic environment it finds itself in. There is also a second mechanism, still more exotic and still more incompletely understood, involving quantum effects in certain photoreceptor molecules in the eyes of birds. These molecules, cryptochromes, appear to produce pairs of electrons whose quantum spin states are sensitive to magnetic field orientation. In effect, some birds may see the magnetic field, not as a separate sense, but as a modulation of their visual experience. A subtle brightness or shadow superimposed on their visual field that shifts in response to the direction of the field lines around them. They may navigate by a kind of magnetic vision that has no analog in any human sensory experience. A perception of space and direction built into the very act of seeing the world. And now consider what happens to these systems in a world where the field is weakening, where the field lines are becoming tangled and multipolar, where the reliable geographic relationship between field inclination and latitude is degrading as the poles drift and the anomaly grows. The evidence that this is already happening is not theoretical. It has been accumulating quietly in scientific literature for years, largely beneath the threshold of public attention. Mass strandings of whales and dolphins on coastlines around the world have been studied for decades without a complete explanation. These events, in which apparently healthy animals beach themselves in large groups, seemingly confused and disoriented, occur with a regularity and geographic distribution that has resisted simple ecological explanations. In the early 2000s, researchers began investigating a potential magnetic connection. Analysis of stranding events in the United Kingdom over a multi-decade period found a statistically significant correlation between mass strandings of certain cetacean species and periods of elevated solar activity, precisely the conditions under which the geomagnetic field is most disturbed. The animals, navigating by a map that had been temporarily scrambled by a solar storm, appear to have lost their bearings in ways that their sophisticated brains could not compensate for. They followed the corrupted map into shallow water and could not find their way back. Solar storms produce temporary disturbances in the field. Temporary and relatively minor compared to what a full reversal transition would involve. And they are already enough, in some circumstances, to fatally disorient animals whose entire navigational architecture is built around field stability. But the disruption to biological systems is not limited to dramatic events like whale strandings. It operates at subtler levels, levels that are harder to measure precisely because they are diffuse, chronic, and distributed across entire ecosystems rather than concentrated in visible catastrophes. Homing pigeon races, competitions in which birds are released at distance and timed on their return to their home loft, have provided inadvertent data on magnetic disruption for over a century. Unusual losses in pigeon races, events in which large fractions of released birds fail to return, cluster statistically around periods of geomagnetic disturbance. The correlation is imperfect and subject to confounding variables, but it is consistent enough across enough independent datasets to be taken seriously. The migration patterns of numerous bird species have shifted measurably over recent decades. Climate change is the dominant explanation for most of these shifts, and rightly so. Temperature gradients drive migration timing in ways that are well understood. But within those broader climate-driven shifts, researchers have begun to identify anomalies that do not fit the climate model. Timing and directional irregularities that suggest navigational uncertainty, as if the magnetic map the birds are reading has become slightly and increasingly unreliable. These are subtle signals in noisy data, and the scientific community is appropriately cautious about overclaiming. But the theoretical mechanism for magnetic disruption affecting migration is solid. The evidence for field disruption is unambiguous, and the precautionary logic for taking the connection seriously is compelling. There is also a dimension of this biological sensitivity that operates at a scale far smaller than birds or whales, and far more fundamental to the functioning of living systems at the cellular level. Magnetotactic bacteria, microorganisms that synthesize chains of magnetite crystals inside their cells and use them to orient along field lines, are among the most ancient forms of life on Earth. They are found in sediments at the bottom of lakes and oceans, where they navigate the interface between oxygenated and anoxic water, using the field's inclination as a vertical guide. Their ecology, their distribution, their functional role in the microbial communities of sediment environments are all organized around the assumption of a consistent, reliable magnetic orientation signal. In a world with a weakening, fragmenting, multipolar field, what happens to these communities? What happens to the sediment chemistry they regulate? What happens to the biogeochemical cycles they participate in? These are not questions anyone can answer yet, because the experiments that would answer them have not been run. The relevant field conditions have not existed in any time during which science was available to observe them. We are reasoning about the potential consequences of a magnetic transition on living systems using analogies, models, and fragments of evidence from events that happened hundreds of thousands of years before the first human being drew a breath. The honest, uncomfortable truth is this: the geomagnetic field is not merely a physical structure that protects the atmosphere. It is an environmental variable, as real and as ecologically consequential as temperature, light, and gravity, that the entire biosphere has been calibrated against for hundreds of millions of years. Every organism that uses it is dependent on its stability in ways that are not peripheral to that organism's survival, but central to it. And the current rate of change in the field, the weakening, the drift, the anomaly growth, is happening at a speed that, while slow in geological terms, is fast relative to the evolutionary timescales on which biological magnetoreception systems were built. Evolution cannot redesign a sea turtle's magnetic map sense in a century. It cannot rewire a bird's cryptochrome-based magnetic vision in a generation. Natural selection operates on timescales of thousands to millions of years. The field is changing on a timescale of decades to centuries. The gap between those rates is where vulnerability lives. And we have not even begun, yet, to talk about the most vulnerable navigator of all. The one that built cities over the coastlines, where the turtles beach, the one that filled the skies with aircraft guided by magnetic compasses, the one that launched the satellites that now web the space above the field that is quietly, measurably, and irreversibly declining. The one that never evolved a magnetic sense at all, and compensated for that absence by building one out of silicon and metal and code, and then made the entire architecture of its civilization depend on that artificial sense functioning in a stable magnetic environment. Us? Always. In the end, us. On the morning of September 2, 1859, the telegraph systems of North America and Europe failed simultaneously. Operators sitting at their instruments reported sparks leaping from the equipment. Some telegraph lines, disconnected from their power sources, continued to transmit messages on their own, powered entirely by the currents induced in the wires by the geomagnetic storm raging above them. The auroras were visible in the Caribbean. They were visible in Hawaii. In the Rocky Mountains, gold miners woke in the middle of the night, convinced by the light flooding their camps that dawn had come early. Compass needles swung wildly and then held positions that had no relationship to geographic north. For roughly 17 hours, the most advanced communications infrastructure on Earth was simply gone, erased by a single solar event whose electromagnetic consequence, the magnetic field, even at its full 19th century strength, could not entirely absorb. This event, now called the Carrington event, after the British astronomer Richard Carrington, who observed the solar flare that preceded it, is the benchmark by which space weather researchers measure catastrophic risk. It is not the largest solar storm that has ever hit the Earth. The geological record, read through the chemistry of ice cores and tree rings, preserves evidence of solar particle events far larger than Carrington. It is simply the largest for which we have direct, detailed human records of the consequences. And those records describe, in the language of 1859 technology, an electromagnetic catastrophe that was, at the time, merely a spectacular curiosity, a wonder of nature that disrupted communications for less than a day and left no lasting infrastructure damage, because the infrastructure of 1859 was not deeply enough integrated with electromagnetic systems to be permanently harmed. The infrastructure of today is a different thing entirely. A Carrington-class event striking the Earth in the present would not be an inconvenience. It would not be a spectacle. It would be the largest technological catastrophe in human history. An event that, according to multiple independent analyses commissioned by governments and space agencies in the last 2 decades, could cause permanent damage to high-voltage transformers across entire continents, disable satellite systems for months to years, disrupt GPS navigation globally, collapse the financial transaction infrastructure that depends on satellite timing signals for synchronization, and leave hundreds of millions of people without reliable electrical power for periods measured not in days, but in months or years. The transformers that sit at the heart of high-voltage electrical grids are not ordinary components. They are enormous, custom-built pieces of equipment, some weighing hundreds of tons, that are manufactured by a small number of specialized facilities around the world. They take months to build and months to ship. There is no meaningful global stockpile of spare large transformers. If a Carrington-class event were to destroy a significant fraction of the high-voltage transformers in North America or Europe, the rebuilding timeline, from order placement to installation, given current manufacturing capacity and supply chain realities, would likely be measured in years. All of this is understood. It is documented in government reports, in academic literature, in the testimony of engineers and space weather scientists before legislative bodies that have, broadly speaking, done very little with the information. The United States government produced a detailed assessment of the risk in 2008. The United Kingdom produced similar analyses. The European Space Agency has published extensive documentation of the threat. Insurance markets have begun to price space weather risk explicitly. The conversations are happening in the careful technical language of risk management and infrastructure hardening, in venues that rarely reach public attention. And every single one of those analyses, every risk assessment, every catastrophic scenario, every mitigation strategy, was designed for a world with the current magnetic field. A field that has already lost 9% of its strength in 170 years. A field with a growing splitting anomaly over the South Atlantic. A field whose poles are accelerating across the Arctic toward Siberia at rates that require emergency updates to the mathematical model underlying every GPS device on the planet. Here is the recursive nightmare at the center of this problem. The very technological systems we would need to monitor, predict, and respond to increasing space weather events are themselves among the most vulnerable to those events. Satellites monitor the sun and provide the early warning data that allows power grid operators to take protective measures before a geomagnetic storm arrives. Those satellites operate in the space environment that the field normally protects, a space environment that becomes more hostile as the field weakens. In a world with a significantly weaker magnetic field, the satellites we would need most urgently to track solar activity would be operating in conditions of elevated radiation exposure that degrade their electronics faster, shorten their operational lifetimes, and increase the risk of catastrophic failure precisely during the storms they are meant to warn us about. The GPS system, the satellite constellation that has, in the last 30 years, been quietly integrated into virtually every aspect of modern logistics, navigation, financial infrastructure, and military operation, is acutely sensitive to geomagnetic disturbance. The signals transmitted by GPS satellites travel through the ionosphere, the charged upper layer of the atmosphere, and those signals are bent, delayed, and scattered by irregularities in the ionosphere that intensify dramatically during geomagnetic storms. Today, this problem, called ionospheric scintillation, is managed through correction algorithms and redundant signal sources. It is a known and bounded challenge. In a world where geomagnetic storms are more frequent, more intense, and less buffered by a weakened field, ionospheric scintillation becomes something far more disruptive. A chronic degradation of positioning accuracy that affects not just aircraft navigation but the precision timing signals that synchronize cellular networks, power grids, and financial exchanges. Consider what it means for a bank transfer to fail. Consider what it means for that failure to cascade across a system in which timing synchronization is the invisible infrastructure of every transaction. Consider what it means for the supply chains that move food and medicine and fuel across continents, to lose the precision navigation that has allowed them to be optimized to margins thin enough that there are no meaningful reserves, no slack, no buffer between the efficiency of the system and the disruption of any significant delay. Modern civilization is not merely electromagnetic in its infrastructure. It is electromagnetic in its metabolism. It consumes and processes and transmits information using systems that are, at every level, dependent on the stable, predictable behavior of the electromagnetic environment around the planet. An environment that is shaped, at the deepest level, by the same geomagnetic field that is currently weakening, drifting, and splitting in ways that no civilization has ever had to navigate. And now, add one more layer. One more turn of the screw that takes this from a serious engineering challenge to something that deserves to be described as a civilizational reckoning. The last 2 decades have seen an unprecedented expansion of humanity's presence in low Earth orbit. Where once the orbital environment was the exclusive domain of a handful of government space agencies operating a small number of carefully managed spacecraft, It is now populated by commercial satellite constellations numbering in the thousands, with plans filed and approved for constellations that would bring the total number of active satellites to tens of thousands within the coming decade. These satellites operate in the zone of the magnetosphere that is most directly affected by changes in the field structure at the surface level. They operate in the zone where the South Atlantic Anomaly already causes measurable damage to electronic components on every pass. They operate in the zone that would bear the first and most severe impact of any significant weakening of the overall field. The commercial space economy, valued in the trillions of dollars and growing, deeply integrated into the communications, navigation, and intelligence infrastructure of every major nation, was built on assumptions about the space environment that are derived from measurements taken during a period of relatively stable magnetic field behavior. Those assumptions are now, measurably and demonstrably, becoming less accurate. The environment is changing, the models are straining, and the engineering decisions made for satellite systems that are already in orbit. Decisions baked into hardware that cannot be recalled, cannot be upgraded, cannot be hardened against conditions that were not anticipated when the hardware was designed, are now decisions we will have to live with for the operational lifetimes of those systems. Every answer generates a larger question. Every solution reveals a deeper dependency. Every layer of resilience we attempt to build rests on a foundation that is, at its most fundamental level, beyond our control, beyond our reach, and beyond our ability to fully understand. The field will do what the field will do. The core will convect as the core will convect. The forces at work here are planetary in scale, geological in duration, and absolute in their indifference to the civilizations that happen to exist on the surface during their unfolding. We are engineers trying to fortify a building while the geology beneath it is shifting, not dramatically, not catastrophically in any immediate sense, but with the patient, irresistible epochal certainty of a planet following its own physics. And the building we are trying to fortify is everything we have. There is a thought experiment that space scientists sometimes use when trying to communicate the strangeness of our current moment to people who have never had reason to think about planetary magnetic fields. It goes like this. Imagine that you are an alien civilization, observing the Earth from a distance of several light years, watching its history play out in the electromagnetic signals it emits. You would see, over billions of years, a planet with a stable, strong magnetic signature. A clear, well-organized dipole field, consistent in its structure, reliable in its orientation, the unmistakable signature of an active geodynamo keeping the planet wrapped in its protective cocoon. And then, in an eye blink of cosmic time, a window of perhaps a few thousand years, invisible from any meaningful astronomical distance, you would see that signature begin to distort. The clean dipole would develop irregularities. The field lines would tangle. The intensity would drop. And for a brief, chaotic interval, the orderly planetary magnetism would be replaced by something messy and multipolar and strange before, if the reversal completed, reorganizing into a new stable dipole, pointing in the opposite direction. From far enough away, from a long enough perspective, this would look like nothing. A barely perceptible flutter in the electromagnetic signature of a middle-aged rocky planet orbiting an ordinary star. A geological hiccup. A rounding error in the long biography of a world. From inside it, from the surface, from the cities, from the satellites, from the bodies of every living organism calibrated to the field's stable presence. It would be something else entirely. No human being alive today will live to see a complete geomagnetic reversal, if one is indeed beginning. The timescales involved almost certainly extend far beyond any individual human life, and possibly beyond recorded civilization as it currently exists. But that is not the point. The point is not what we will personally experience. The point is what is already in motion, what has already begun, measurably, observably, in the data that our instruments are collecting right now, and what that beginning implies for the arc of time that stretches ahead of the species, ahead of the civilization, ahead of every choice we make about how to build and how to prepare and how to think about the future. Consider the ozone layer. The connection between the geomagnetic field and the ozone layer is not widely known outside the specialist literature, but it is real and it is consequential. High-energy particles from the sun and from cosmic rays, when they penetrate the upper atmosphere, which they do more frequently and with more intensity in regions of weakened field, and which they would do globally and continuously in a world with a field reduced to reversal transition levels, catalyze chemical reactions that destroy ozone molecules. This effect is measurable today in the South Atlantic Anomaly region, where satellite instruments have recorded elevated rates of ozone depletion in the upper atmosphere directly above the zone of weakened field. It is not dramatic. It is not visible from the surface. But it is there, and it is consistent with the physical mechanism, and it provides a small, present-day preview of a process that would operate at global scale during a period of extended field weakening. The ozone layer absorbs ultraviolet radiation from the sun. It is the reason that life on land exists in the form it does. Without ozone shielding, the UV levels at the surface would be sufficient to damage DNA in exposed organisms at rates that would make the current biosphere impossible. The ozone layer nearly did not survive the second half of the 20th century. The chemical assault from chlorofluorocarbons brought it to the edge of a collapse that would have fundamentally altered the habitability of the planet's surface, and only an extraordinary act of global political coordination, the Montreal Protocol, reversed the damage in time. That crisis was caused by human industrial chemistry and was, in principle, solvable by human decision. The ozone depletion that would accompany a significant weakening of the geomagnetic field is not caused by human activity and is not solvable by human decision. It is a physical consequence of removing the electromagnetic barrier that deflects the particles that would otherwise catalyze the ozone-destroying reactions. You cannot legislate the solar wind. You cannot regulate cosmic rays. There is, admittedly, a great deal of uncertainty about how severe this effect would be during a reversal transition. The atmosphere is not helpless without the magnetic field. It provides its own shielding through density and chemistry against lower energy particles. The question is, how much additional radiation burden would be added by a field at 10% of its current strength, and how the biosphere would respond to that additional burden over the centuries or millennia of the transition? The answer, again, is we do not know with precision. What we do know is that the mechanism is real, that the current field is already weakening, and that the South Atlantic Anomaly already provides a small-scale, low-intensity demonstration of exactly the kind of atmospheric chemistry that would intensify across the entire planet during a prolonged field reduction. But perhaps the most philosophically unsettling dimension of this entire situation is not the ozone chemistry, or the satellite vulnerability, or the biological disruption to migratory species. It is what the weakening of the field does to our understanding of time. Not time in the abstract philosophical sense. Time in the very concrete, civilizational sense of how we orient ourselves in the future, how we plan, how we build, how we invest, how we make collective decisions about infrastructure and risk. Human institutions are not designed to think on geological timescales. Governments plan in electoral cycles measured in years. Corporations plan in fiscal cycles measured in quarters. Even the most forward-thinking infrastructure investments, the building of dams, the construction of nuclear power plants, the laying of intercontinental communication cables, are planned on horizons of decades, occasionally a century. The geological processes that shape the magnetic field operate on timescales of thousands to millions of years. The gap between these scales is not merely a technical challenge, it is a structural mismatch between the speed of human institutional cognition and the speed of planetary physical processes. And yet this mismatch is not entirely unique. Climate change presents a similar structural challenge, a planetary process unfolding over timescales that exceed normal institutional planning horizons, demanding action in the present to prevent consequences in a future that no current decision-maker will personally inhabit. The response to climate change, with all its difficulty and political friction, represents the beginning of an attempt to stretch institutional thinking across that gap. The response to geomagnetic risk, to the possibility of increasing space weather vulnerability, to the fragility of electromagnetic infrastructure in a world of declining field strength, has not yet reached even that beginning. There are scientists who study this. There are engineers who take it seriously. There are government reports, as mentioned, that document the risks with careful specificity. But there is no Montreal Protocol for the magnetic field. There is no global framework, no coordinated investment strategy, no common technical standard for infrastructure resilience against space weather at the scale that the risk arguably justifies. The risk is understood, in fragments, by specialists. It has not become part of the shared public understanding of what the future might hold. But another part of the reason is something deeper and more human. It is the fundamental difficulty of taking seriously a threat that operates on timescales longer than a lifetime, that is invisible to direct sensory experience, that has no historical precedent in the memory of any civilization, and that arises not from anything any human has done, but from the autonomous, indifferent physical processes of the planet itself. It is easier to ignore. It is easier to assume that the way things have always been is the way things will continue to be. It is easier, in short, to live inside the fortress without inspecting the walls. And yet the walls are there. The data is there. The instruments are reading, continuously, the slow and patient language of a planetary process that does not care whether we are listening, does not care whether we are ready, and will proceed at its own pace regardless of our preparedness or our politics or our preferences. The universe did not design itself around our convenience. The Earth did not promise us stable magnetic conditions in perpetuity. The field has reversed before, and everything that lived through those reversals, every organism, every ecosystem, every biological system with a magnetic sensitivity, had to manage without any warning, without any preparation, without any technology to compensate for the disruption. We have something those organisms did not have. We have knowledge. We have instruments. We have the ability, unique among all the creatures that have ever lived on this planet, to read the signal before the consequence arrives, to see, in the declining field intensity and the drifting poles and the splitting anomaly, a message from the deep interior of the Earth written in a language that took us centuries to learn to decode. The question is whether knowing is enough, whether reading the message is the same as responding to it, whether a civilization capable of detecting a planetary transition in its earliest stages is also capable of doing something with that detection beyond documenting it in journals that most people will never read and reports that most governments will never act on. That question has no guaranteed answer. It is, in the most direct sense, still open. And its resolution, whatever form it takes, will say something profound and permanent about what kind of civilization we actually are. Not what we claim to be, not what we aspire to be, what we actually are when the planet itself presents us with a problem that exceeds the span of any individual life, the horizon of any electoral cycle, and the ambition of any quarterly earnings report. The signal is clear. The message is being delivered. Whether anyone is truly listening is still entirely up to us. Somewhere beneath you, right now, the iron is moving. Not quickly, not with any urgency you could detect if you pressed your ear to the ground or drove a spike into the bedrock or descended as far as any human instrument has ever reached. The movement is measured in centimeters per year, slower than your fingernails grow, slower than the continents drift apart, slower than almost any process you could name that still, over time, reshapes the world. But it is moving. The liquid iron of the outer core is convecting in great slow thermal plumes driven by the heat of radioactive decay and the slow crystallization of the inner core growing outward into it, millimeter by millimeter, over geological time. It has been moving for 3 billion years. It will continue moving for billions more. And as it moves, it carries electrical currents, and those currents generate the field, and the field reaches outward from the planet's surface into space. And in space, it deflects the solar wind, and in that deflection, in that silent, invisible act of planetary self-protection that happens 65,000 kilometers above your head at this very moment, it makes everything possible. Everything. Not metaphorically. Every breath of oxygen you take exists because, in the absence of the field, the molecular hydrogen in water would have been stripped from the upper atmosphere by solar radiation over geological time, leaving nothing but a thin envelope of heavier gases and an irradiated surface. The oceans you depend on for the hydrological cycle that produces rain and fills rivers and grows crops. The oceans exist in the form they do, partly because the field has preserved the conditions under which liquid water can persist on this surface for billions of years. The entirety of biological evolution, the 4 billion-year cascade of increasingly complex chemistry that produced, as one among countless experiments, the nervous system you are using to process these words, happened inside the shelter of this field. You are not merely protected by it. You are, in a very real sense, a product of it, a consequence of its presence. One of the things that became possible because it was there. And now you know that it is not permanent. You know that it has reversed before, hundreds of times, across the long and mostly uninhabited biography of this planet, and that it is, by every measurement we are currently capable of making, in a state of change. Not catastrophic change, not imminent collapse, but measurable, directional, accelerating change that no honest reading of the data can interpret as stable. What do you do with that knowledge? This is not a rhetorical question. It is the question, the only question, that ultimately matters in the face of any discovery that reorients your understanding of the ground beneath your feet. And the history of such discoveries suggests that what most people do, initially, is nothing. Not out of indifference, exactly, but out of a very human incapacity to translate abstract systemic risk that is geological in scale, invisible to direct experience, and uncertain in its timeline, into felt urgency. The brain did not evolve to respond emotionally to gradients. It evolved to respond to immediate threats, to sudden changes, to the predator emerging from the tall grass. A planetary magnetic field declining by 9% over 170 years does not trigger the same neurological alarm as a predator. It does not arrive with teeth. It arrives with data. But data, for those willing to sit with it long enough, has its own kind of teeth. Consider what it means that we are the first species in the history of life on Earth to be capable of knowing this is happening. Every organism that lived through every previous reversal, every bacterium, every trilobite, every dinosaur, every mammal that navigated by field lines in the eras before ours, passed through those transitions in complete ignorance, They did not know the field was weakening. They did not know that their navigational systems were becoming unreliable, or that the ozone layer above them was thinning, or that the auroras now appearing at equatorial latitudes were symptoms of a planetary electromagnetic transition. They simply lived and adapted and died and were succeeded, as they always had been, by whatever came next. We are different, not morally superior, not inherently wiser, but structurally different in a way that is genuinely unprecedented in the long history of life. We can read the planet's signals before the consequences arrive. We can measure the field. We can track the poles. We can watch the anomaly grow and split in real time from satellites whose entire operational existence spans less than a geological instant. We can understand, at least in principle, the mechanism generating the changes we observe, the convecting iron, the thermal plumes, the deep structural anomalies in the lower mantle that bias the flow and nudge the field toward instability. We can do all of this. Whether we do anything useful with the ability is a different question. And it is a question that opens onto something much larger than the magnetic field itself. Something that has been, in one form or another, the defining question of the entire modern scientific age. What is knowledge for, if not for preparation? What is the point of reading the planet's signals if the reading never changes the behavior of the civilization doing the reading? There is no comfortable answer. There is only the honesty of the question and the space it opens. Because here is what the science of the geomagnetic field ultimately teaches, if you follow it all the way to its implications without flinching. It teaches that the stability you have always assumed is not a permanent feature of the universe. It is a condition, a specific set of physical circumstances that happen right now to be favorable for the kind of life you represent. Those circumstances are not guaranteed. They are not the default state of the cosmos. The cosmos does not have a default state that is hospitable to life. Life, wherever it exists, is a local and temporary exception to the general indifference of physics, a highly improbable arrangement of matter and energy that persists only as long as the conditions that allow it persist. And those conditions are subject to change. Not human change, not political change, not economic change, but planetary change, stellar change, cosmic change, operating at scales of time and energy that make the entire span of human civilization look like a single afternoon in the biography of the universe. Mars understood this in the only way a planet can understand anything, by losing its dynamo, by letting its interior cool below the threshold at which convection could sustain the geodynamo, by allowing the solar wind to do, over billions of years, what the field had previously prevented. The thin atmosphere that remains on Mars today, less than 1% of Earth's atmospheric pressure, unable to support liquid water, unable to shield a surface from radiation, unable to sustain the chemistry of life as we know it, is what the end of a magnetic field looks like on geological timescales. It is not dramatic. It is just slow and thorough and final. The Earth is not Mars. The Earth's interior is still hot, still convecting, still generating the dynamo. The field is weakening, but it is not collapsing on any timescale that current science can identify as human relevant. The message written in the declining intensities and drifting poles and spreading anomalies is not a message about extinction. It is something subtler and, in some ways, more profound. It is a reminder that you live on a planet with its own physics, its own rhythms, its own cycles of stability and transition that have been unfolding since long before you arrived, and will continue unfolding long after every trace of your civilization has been absorbed back into the rock. A reminder that the invisible systems sustaining your existence, the ones you inherited without negotiation, without awareness, without gratitude, are not permanent infrastructure. They are temporary gifts from a universe that mostly does not know you exist. A reminder that the appropriate response to living inside a finite and dynamic planetary system is not complacency, but attention. Not fear, but curiosity. Not despair at the limits of what you can control, but a kind of reverent seriousness about what you can know, and what you can do with that knowledge, while there is still time to do anything at all. The iron is moving beneath you right now. The field lines are shifting, slowly, at the edges of detectability. The anomaly is growing. The poles are drifting. 3,000 kilometers below your feet, in temperatures that would vaporize anything you have ever built, in pressures that transform matter into states without familiar names, the ancient engine of the planet is doing what it has always done, following the laws of physics across timescales that make human ambition seem, from a sufficient distance, almost unbearably small. And yet, from inside that smallness, from within the brief and improbable window of awareness that biological evolution accidentally produced on the surface of this particular planet, you are here, reading the signals, asking the questions, capable, at least in principle, of caring about a future you will not personally inhabit, for the sake of a civilization you did not personally build, protecting a biosphere you did not personally design. That capacity, the capacity to care about what happens after you, is perhaps the strangest and most extraordinary thing the universe has ever accidentally made. Stranger than the geodynamo, stranger than the field itself, stranger, even, than the billion years of slow geological pressure that may now be expressing itself as a split anomaly over a remote stretch of ocean. The planet has been here before. It will be here again. The question is what we choose to be in the thin and luminous moment between the one and the other.